Thank you. Thank you. Thank you, everybody. It's a real pleasure to be here. I almost had a heart attack yesterday when I realized this is an in-person seminar. So I was like, how does that work? So I completely forgot. It's a real pleasure to be here. I'm the recovering physicist at Kellogg, where I lead the Center for Science of Science and Innovation, which is dedicated to this emerging area that many of us now call science of science. So what I'm going to do today is first give you a 1-minute intro of what science of science is about. So I would say 2018 was a pretty exciting year for the field, where we published the first review paper of the field called Science of Science in Science. Later that year, Science also put us on the cover issue, a special issue to talk about arguing toward a more scientific science. Earlier this year, we also are excited about the publication of the book of the field called The Science of Science that was published in Cambridge University Press. So in many ways, this idea of turning the scientific methods and curiosities on science itself, this is not a new idea. This idea dates back to at least the mid-past century. There are several founding giants of the field, such as Robert K. Morton, the great sociologist of science, thinking about the idea of Matthew effect, singletons and multiples. Or the Price, like physicist turned historian of science, thinking about the idea of invisible college, power laws, cumulative advantage. Or Harriet Zuckerman, another sociologist for science, thinking about an ethnography approach to understand scientific careers. Or, Eugene Garfield, the information scientist, is thinking about the citation index. Or, of course, there's Thomas Kuhn, one of the greatest thinkers of the 20th century, thinking about the idea of paradigm shifts. So in many ways, I think the recent surge of interest in understanding science basically wanted to stand on the shoulders of these giants, but then take two things that they did not have the luxury to have in their time. First is a massive amount of data sets that captures the entirety of the scientific enterprise, that captures the inner workings of science at a new level of scale and detail. And second, and just give you a sense of this new available large-scale data sets. So how much is new available? I look back my group's research over the past 5 years. I think it's very safe to say every year our research agenda is surprised or disrupted by a new data set that we didn't even think was possible a year before. It was true this year, it was true the year before that it was also true. So. And at the same time, there's a parallel development. The second factor is there's a parallel development in fields like complex systems, network science, data science, and artificial intelligence, which offers a wide range of tools and techniques that help us make sense of this data with growing accuracy and robustness. And what we realize is that together, this data and new tools can help us tell a very complex but insightful story about how innovative careers unfold, about how people come together, collaborate, and contribute to discovery, and about how scientific progress may emerge from multiple interconnected factors. So when Julio asked me, I was thinking, what can I do in this seminar? I thought, it's useful to think about the consumers of this kind of research. Who will benefit from this research? There are several different audiences that are benefiting from this field. One type of audience would be decision makers, including people like Julio, your deans, department chairs, VPs of research. Also includes the program directors from NSF, NIH, private foundations, philanthropies. These people are making strategic hiring personnel and investment decisions to think about how to advance science. So these people, I think, hopefully what the insights produced in the field are useful for these people. At the same time, these are also could be useful for everyday scientists, as we all think about what are the mechanisms that govern everybody's passion, that is science. So specifically to that context, I was thinking maybe I'll select a few insights that will speak to directly the second audience I just described, with the understanding there are a whole bunch of other things I'm ignoring. And what I'm going to do today is to go through, I think, roughly 3 to 4 different areas. Hopefully, it will take away about 4 to 5 different lessons if you walk out of here from today. And I'm going to pick this research in a way that will hopefully give you a diversity of different areas, so help you understand a little bit of the flavor of type of research that we do here. But at the same time, I will given that this is sort of more general audience, so just with the understanding, there will be a lot of simplifications as I present this research. But hopefully, luckily, in this case, I'm going to be mostly presenting published work. So there will be supplementary information if you want to learn about more details. Okay, so let's get started. First, I want to think about this question that has fascinated me from the very beginning, which I call the hope project. So the idea is I'm observing all these kind of very successful careers around me and in the history, and I want to ask, are there patterns of a promising scientific career? So this is why I call it a hope question. Is the main question I was really interested from when I was a grad student was, when do you do your best work across your career? And is there hope left? After a major discovery, will you produce another big breakthrough? Okay, or are we dead, scientifically speaking? So one way to think about a scientific career is to simplify them into what I call a drop pin view of a career. In this case, every time you publish a paper, I put a drop pin there, and the height of a pin will tell me how good these papers are, approximated by citations after adjustment for your field, for example, right? So once I have this, then I can actually measure across thousands of careers I have in my database, when do you actually do your best work in this case, okay? So this is a question that has fascinated economists and psychologists for several decades. And the conclusion, overarching conclusion is very robust. Is you will see some pattern like this. That is, you do your best work somewhere in your mid-career. And the logic goes as following. There is no 4-year-old has ever won the Nobel Prize because in the beginning you have to learn. As you get older, then, after you pass the mid-career, there's a growing responsibilities and duties, administrative duties, all of them pile on your shoulders, reduce your time for breakthrough, okay? So we measure something that in our data looks like something similar here as well. And I think in particular for people that are already mid-career in the audience, you will notice this gradual, if brutal, decline after you pass mid-career, okay? So what we wanted to do is to say, let's not argue about the shape of this distribution. Let's do a simple experiment with our data, since we have so much data. Now, what if I take all these drop pins in each career, I start swapping them, okay? So I take 2 job pins, I'm going to swap their location. 2 job pins, I'm just randomly create a shuffled version of a career, okay? So as I'm swapping them, what am I doing? I'm not taking away any pins, so I'm not changing your productivity. I'm not changing the distribution of the height of the pin. All I'm doing is like a deck of a card. You have an ace in that card, I now shuffled it, okay? Now we're going to measure when do you do your best work in all these randomized careers, okay? Now I plot right on top of this distribution. What do you see? In the shuffled careers, you also see basically the same pattern, okay? So what this means is what discovered, reported in the paper, is called a random impact rule. So what this says is that, you do your best work in your mid-career. It's not because age and creativity are intertwined. It's really just because you produce more during your mid-career, okay? So before I get too excited, let's actually push on the robustness of this finding. So what we did is to say, first of all, let's extend this finding, not just for scientists, look at other different but related careers. For example, think about all the artists. So we collect the data for the past 500 years of the artists. So look at artists' careers in terms of the artwork they produce and auction prices of those artworks. Look at all the movies on the IMDb database, looking at all the directors and the movies they produce and the IMDb ratings of those movies. And for all these careers, I can look at when do you do your best work. I'm going to plot that in the cumulative distribution of where does it happen within the sequence of work you produce. You see a clear signature that follows a diagonal pattern. So this means your best work has equal probability within the sequence of your work. It can be maybe your first work or very last work or somewhere in the middle. We don't have to stop there. We can say, okay, so what about your second best work? What about your third best work? What you see here is that no matter how we look at it, despite the diversity of careers we study, there seems to be a remarkable consistency across these careers. Yeah, these are distributions, right? So. Right. So these are distributions. So basically, you're sort of measure, sort of think about K as difference from null distribution, which is random. So, yeah. So and then so this sort of if you just stop here, a lot of people characterize this sort of called me Mr. Hopeful, because it seems like what it offers a rather hopeful message for people is that there is this. It's true as you get older, your chance to break through start to dim, but that's not because you're less creative. Per paper, your hit rate actually stays remarkably constant through your career. So some people tend to take this as a message of as long as you keep producing, your best work may be yet to come. Okay? So, but at the same time, this also raises a very big puzzle to me, is that this looks to me is like across all these careers, it's like a lottery ticket. Every time you go draw a lottery and see if it's going to hit or not. Okay? Now the question is, what happens when you make a big hit? Okay, if I had a big hit, I would want to think, okay, I got some recipe that I figured out, and I'm going to be able to reproduce it. Or it puts me on the map. More people will know me. So maybe, that will help me to do all of or attract more students, better students. All of this should help me do a bigger hit. But what this is showing me is that everything's like a lottery ticket. So you actually, after your best work, your next work is more likely to be mediocre than spectacular because of regression toward the mean, right? So what exactly is going on here? It turns out the puzzle cracked open when we look at the timing of your best work and your second best work. Okay, what we're seeing here is a clear diagonal pattern. So what this is telling me is that if I know where your best work is, I know very well your second best work is, it's just around the corner of your best work. Similarly, you can look at, okay, what about the second and the third best work? Every time you look at this, all the top career hits, you see they all cluster together. So what this means is that, well, the timing of each your scientific hit appears random by itself. The relative timing, however, follows rather predictable patterns. You can also ask, okay, do these hits actually come back to back close to each other through streaks? So you can also measure, okay, how many of the great works come together as back-to-back in sequence, and compare it with randomized careers. You see real careers are systematically characterized by winning streaks that high-impact works occur in sequence. Now the question is, okay, what mechanisms are responsible for this observed clustered nature of hits in individual careers? What we find is that the most likely explanation is that ubiquitous but rather unique house streak period that emerges randomly in a career. The way you want to think about this is that imagine you start your career at a certain level. Every time you publish a paper, you draw from a certain distribution, and that will be the type of work you tend to produce. Okay, you progress along that level, and then at a random point in your career, all of a sudden you elevate it to another level. It's like you're not yourself anymore. It's like you went Super Saiyan, if you know the Japanese cartoon. And then you stayed at that level for about 4 to 5 years, and then you fall back to where you were before. So, and what we find, what's interesting is if we just assume this very simple variation in your career, and assume that it emerges randomly within the sequence of your work, you will realize it explains all the observations that I just showed you. Okay? But what's really interesting then is that we can fit this model to real careers and actually learn a little bit about what are the properties of house streaks. Okay? Once we do that, we see a couple of interesting takeaways for you guys. First, we see that house streaks are very ubiquitous. Across all 3 domains, artists, directors, and scientists, about 90% of people have house streaks. But it's usually unique. Most people have just 1 house streak. People who have 2 are much less, and people who have 3 are exceedingly rare. Okay? Second, what we find is house streaks doesn't last forever. It lasts about 4 to 5 years across these 3 kind of careers. And also, it appears unassociated with any productivity change. In other words, you don't really produce more than we would expect otherwise. But just what you produce during this period seems to be substantially better than what we would expect typically. Oh, yeah.
So one potential disadvantage of using a large data set is that you're measuring the properties of average people, right? So the randomness might be just because of the fact that you have thousands of average scientists. Mm-hmm. What if you only look at Nobel Prize winners? Would they have similar distribution?
Great question. This is the week a lot of our work. So some of our work has got picked up at a yearly cycle, and this is the week where we got picked up. And we had a paper in Nature Review Physics where title was to say, Nobel Prize winners are almost just like us. If you repeat Nobel Prize winners, what you see is that the Nobel Prize winning work, these proportions will occur very early because you have to be alive when you win the Nobel Prize. But if you look at the most cited work within the Nobel Prize career, you see again the same pattern. That is very interesting that we discover, actually, you look at all the Nobel Prizes have been awarded to physics, chemistry, and medicine, and they all follow the same pattern that as a normal scientist that we observed. So that's another. So yeah, so that's a hopeful. But then sort of.
Engineering doesn't have a Nobel Prize, right? So in some ways, what would be the one on the technology innovation side that would be maybe not now?
So you mean the engineering careers?
Yeah, engineering careers, because they are more not about a breakthrough per se, but making things better, right?
I see. So clarification, the scientist sample does include engineering. Yes. Okay, got it. Yeah. All right. So, hot streak, then once we discovered it, is obviously a concept that seems important to think about science decision making, because in science, the projection of future impact is very important for hiring, promotion, tenure, as well as investment in research. So what this tells us is that if you want to capture an individual's future impact, you ought to take into account the hot streak in your calculus. And especially if you ignore hot streak and as well as a singular nature, it may lead you to over or underestimate an individual's future potential. But a crucial question remains is that what is the mechanism for hot streak? To me, this is an essential question, and this is a question that I raised shortly after the publication of the Nature paper in op-ed to Wall Street Journal, is to say, is there any identifiable regularity around the onset of hot streak? And the reason I think this is crucial is if we understand this question, it will help us answer a range of new questions. For example, can we anticipate the beginning or the end of a hot streak? Can we create an environment that will facilitate the onset of a hot streak and to extend it when it emerges? And for someone who has had a hot streak, can we treat it as an indication of that person's potential and then help that person realize that potential again, okay? And this is the question we've been hammering away for about 3 years, and I'm super excited. The answer just emerged 2 weeks ago. So, and we tried to answer this for a very long time, but the aha moment really came when I was visiting Amsterdam, the Van Gogh Museum, and I was walking through the gallery, and I know Van Gogh is a data point in my sample. His hot streak happened at 1888 when he moved from Paris to south of France. As I was walking around the museum, I sort of see, there seems like before that period and after that period, there's some characteristics change in terms of the painting that he produced. That got me thinking, if we want to understand what happens before and after hot streak, we ought to look at what exactly was the work that was produced before and after. So this got us to collect a set of all new data sets, including all the images of artwork we produce. In this case, include 800,000 different artworks that we can collect everywhere online. As well as for the movies, we look at about 80,000 plots and the casts in those movies to look at what this movie is about. And also for scientists, we have about 1 million publications to look at what these works are. For each of them, we have to design specific algorithms to help us understand, because 800,000 images clearly is not something we can go through one by one. In this case, for example, deep learning to the rescue. So basically, we use a VGGNet algorithm and repurposed it to classify art style labels. And then in this case, what we do is that once we repurpose it and predict well the art style labels, we start to look under the hood, look into different layers of this deep neural network. So if you look at lower layers of this VGG net, the convolutional layers, you see they capture low-level features such as line orientations or brush strokes. Look at the higher level layers, what you see is that it captured higher level features like objects or styles. And this sort of tells you roughly what this neural network is seeing from this painting. And then we can sort of basically have this high dimensional embedding of artworks that help me tell me what this artwork roughly is about. Similarly, you can do that for movies by looking at the plots of a movie and think about word embedding of those plots and tell you what these scripts are about. And then you can look at also casting information and use a deep walk around the co-casting network to tell you who are the casts in this movie. And combine these vectors, you again can have a very high dimensional embedding space of each movie to tell you what this movie is about. And then you can look at the same thing for scientists, where you can look at all the references were cited within each publications and see what this paper is about. Okay, once we apply all that, then we can basically start testing a hypothesis that I had, which is to think about of myriad factors that may affect career progression and success. This idea of exploration, trying different things, and exploitation, be very focused and work on just one thing. This is an idea that has attracted multiple disciplines for over the past several decades. So the question is, are career health streaks reflective of exploration or exploitation? So what we can do then, just align everybody along when your health streak occurs. Look at what did you produce before and what did you produce after, and then look at the entropy of these works that you produce, okay, on the clustering of the high-dimensional space. What we see here is very simple 3 messages in this figure. First, what we see is that before the health streak, your entropy is systematically larger than we would expect comparing with your randomized careers. So indicating that before health streaks emerges, individuals tend to explore different styles and topics, try different things. After health streak begins, shortly after your health streak, what we see is that your entropy now becomes systematically lower than expected. That it seems like very exploitative, tend to be exploiting one, be very focused on what you work on. Okay. Third is that despite the diversity of domains we study and the differences in methodologies that we study these careers, what we find is this relationship between exploration, exploitation, and health streak appears rather consistent across all these 3 domains that we study. So what's important is to think, it turns out actually neither exploration nor exploitation alone is associated with health streak. It's really this exploration followed by exploitation that's consistently associated with the onset of health streak. Okay, so this one plausible explanation of this is to think about exploration as a risky variance enhancing strategy, allows you to try different things and stumble upon groundbreaking new ideas. And exploitation allows you to build on this idea and build out this discovery further. Okay, so this also supports the notion that not all explorations are fruitful, and exploitation in the absence of great new ideas may not be as productive. By contrast, this exploration followed by exploitation can allow an individual to incorporate new insights into a focused agenda. So this position of exploration before exploitation then help you expand your creative possibilities. Okay, so this is something sort of overall, like taking into account the first major lesson for everybody here is first, there is a hope, to recap. I think what I would like to think about all of this through the first figure I showed you, which is John Fan, who at the age of 70, roughly 70, was forced retired from Yale because he's been pottering around without really producing anything. But he said, fine, and he left Yale and set up shop, a new lab in Virginia Commonwealth University. And that's where you will see, that's where his health streaks start to emerge, produce one after another, that eventually the work he did about electron spray ionization eventually won him the chemistry Nobel in 2002 at the age of 92, right? So So I think what this sort of the randomness in when the house streak occurs within your sequence of work, it can be a very hopeful message because the conventional wisdom tells us that you do your best work somewhere in the mid careers. As you get older, it seems like it become less hopeful. But what this is saying is that while we may not have the Einstein or Fence-like impact, but your miracle year may be still ahead of you. It's just out of sight. Okay? And then when that happens, remember this idea of exploration followed by exploitation. And that's hopefully that will be helpful for all of you as your house streak begins. So that will be the first set of data I want to show you. But I now want to challenge the entire thinking of that by presenting to you a new fact. That is, today, great discoveries no longer emerge from lone geniuses working by themselves, making guiding contributions. Rather, high-impact science increasingly emerge from a complex network of innovators working together in teams. So I'm going to quote you one of the most canonical papers in my field. It was also produced here by my colleague Brian Huzi and Ben Jones back to 2007, where they document a remarkable fact that is one of the most universal shifts in science and technology today is the growth of large teams in all areas of research as solitary researchers and small teams diminishes. So this makes me wonder, what are the, so individual careers is not just about an individual, it's about how you collaborate with people. So this makes me wonder, what are the organizations of the innovative activities? What configuration of the teams that are best positioned for innovation, okay? So this movement towards larger and larger teams, there's a poster child for this. The example will be the Ligo Experiment, which is the largest project ever funded by NSF. It was with the detection of gravitational waves, was coined the discovery of the 21st century, and won the Nobel Prize 2 years after the discovery. When the paper was published, it has more than 1,000 authors on it. Okay, as a former physicist, people say I got a little too excited when I talk about this. But think about what they did here, right? Build this 2 arms of 4-kilometer long tunnel, housed in ultra high vacuum to detect a variation that's a trillionth of an inch. Okay, so this is obviously a celebration of large, big team science. It's something that no small teams will ever hope to pull off, right? So, but at the same time, there are reasons to believe that large teams may not be optimized for innovation. Because large teams, just like large business organizations, tend to focus on sure bets with existing markets. Okay? Whereas small teams with more to gain and less to lose may more likely to undertake untested opportunities. So this makes me wonder, along with my collaborators, the simple question is bigger always better? Okay? So we look at this again through 3 different domains, including 43 million papers, teamwork reflected in these papers, about 5 million patents, inventions, teamwork, about 16 million code bases, teamworks of software projects. And across all this, we want to measure one measure that has already existed in the literature called the disruption index. So the idea is, to what degree this work you produce open new areas of research for people who follow, or this is just amplifying what was known before. Okay? The way you can measure this is to think about this focal work. Out of all the future work that cite you, do they also cite the work that you cited? Okay? In this case, D = 1 means all the future work cite this work, they ignored everything that came before, just cited this work alone. So this means this is it basically eclipses the literature that came before this paper. Or for here, all the papers that cite this paper, they also cite what happens before. So you're really amplifying, developing the existing school of thought. Let me give you 2 concrete examples. Think about this example, BTW model paper, which is a foundational paper in complex system, thinking about the self-organized criticality. About 3,000 citations, but all future papers cite this paper, just cite this paper, ignores everything came before. This paper, Davis et al., is what won often a Nobel Prize in physics. It's an empirical demonstration of Bose-Einstein condensation. It's a Nobel-winning paper, but for all the future papers, about 3,000 of them, same number. When they cite this paper, they also cite what came before, namely Bose-Einstein condensation. So what we call this paper is very developmental. So the question then is, small and large teams, which is more developmental, which one is disruptive? So we plot these curves across all three domains. We're seeing a nearly universal pattern, namely the red curves all going up, the green curves all going down. Okay? The red curves means the citation impact of the work. And this is consistent with prior literature, is as your team gets bigger, the impact of work your team produces tend to become higher. And this was the promise of we need bigger and bigger teams. But as we're looking at your disruptive index, what we see is that as your team goes bigger, the disruptiveness of the work you produce systematically decreases. So what this means is that whereas large teams tend to develop on further existing ideas and designs, small teams are the ones that are more likely to disrupt current ways of thinking with new ideas and opportunities. In other words, large teams excel at solving problems, but it's the small teams are the ones more likely to come up with the new problems for them to solve. So now go back to my Ligo experiment, you start to realize, yes, Ligo was the discovery of the 21st century, but it was a careful demonstration of the discovery of the 20th century. When Prussian Academy of Science first heard the highly disruptive theory of general relativity that predicted the existence of the gravitational waves, it was in November 1915, exactly 100 years before the detection of gravitational waves. So the idea, it was proposed by the ultimate small team, this one single individual. So the idea of the theory of gravitational wave and this detection both move science forward, but they do so in very different ways. So then the big takeaway here is to think about this idea that both small and large teams are important for advancing science and technology. Okay? Small teams are really good at coming up with new problems and disrupt current ways of thinking, but large teams can then pick up the ball and engage in further development of these ideas. Together, small and large teams can form a sort of together as an ecosystem of the overall virtuous cycle. And this was why the idea from Nature put us on the cover in thinking about the ecology of research, when you have an ecology of both small and large teams together. Okay, so this is the main lesson, is to think about, okay, bigger is not always better, and hopefully this lesson, has been very useful for me. Hopefully it's useful for you as well, because as someone who manages teams on a daily basis, I used to think, as a collaborative person, I used to think, why not add another person to the team? That person may not help, but it shouldn't hurt. But what this research is telling me is that that's not true, because it depends on what kind of work you're trying to do. If you're locking into a larger team than you should have, it likely shifts your process and outcome from developmental to disruptive. So depending on the work, the really innovative work, you might actually consider to shrink the number of people to engage in the beginning. So hopefully this is something that will be useful for you as well. Now, yes? So this small team and large team discussion was primarily actually being picked up in the funding domain. And one of the results I didn't mention is, this shift before this results, this shift become to larger and larger teams across the sciences is almost becoming self-fulfilling, in the sense that the research shows when NSF evaluate both two teams that are equally capable, they're more likely to select on the larger teams on the premise that larger teams with more minds and brains and muscles are always going to be better. So, but what this is sort of challenging is sort of thinking about funding science is really the first question is what kind of science we're talking about. Is this a disruptive theory of gravitational waves or an empirical demonstration of that theory? So that's hopefully that sort of touches on this point.
Yeah, I know this Ligo history very well.
Yes, correct. I think that that basically is consistent with what we're finding is if you think about for an NSF to invest $1 billion over 40 years, you better have some sense that you better have a clue already what you're trying to do. And that's what we're trying to say is relates to the nature of the type of work that you do. This is the large, big team type of work, but big team is not always optimized for innovation because for a crazy theory, for 1,000 people to all buy in and say, let's do it, then it's not a crazy theory anymore, right? So I think that's what we're saying in this case. Okay, all right. So now I'm going to turn everything around is to think about, as we were looking at all the successes of individuals, teams, and the ideas they produce, I started to realize there's a big problem with all this research, my own research. That is, there's a big elephant in the room, namely failures. In other words, I start to realize a lot of our insights about careers, teams, are all based on individuals and teams who have succeeded at the first place. But at the same time, for every individual here, there are thousands, if not millions of others who failed and disappeared from the scientific record. So this became a big problem. That's why about 3 years ago, I told my group, I'm going to look at failure from now on and no longer look at success. And for like 3 months, nobody believed me until they realized I was serious. And let me illustrate to you why I think this is a big issue and why we really need to pay attention to failure. And this example that some of you may be familiar with is to think about this example through World War II in British Navy. Back then, the British Navy invented this new armor. And the good thing with this armor is you can pat it on a plane and make the plane bulletproof. Okay? The problem with this armor is that it's quite heavy. So you can't put the whole plane because then the plane, you can't coat the whole plane. The plane can't take off. So the question is, where do you put it on the plane that will give you the biggest bang for your buck? So, British Navy was no dummy, and they had an R&D department. They said, well, let's not have individual biases get in the way. Big data to the rescue. Let's go to our airports and count bullet holes and see where we have the greatest density. Okay, once they do that, they have a plane that looks like this. So they almost went ahead with the plan until Abraham Wald, the statistician in the R&D department, stopped them and said, guys, I think what we should do is the complete opposite. Because in this case, the data is collected based on planes that were successful enough, got back to the base. So the places where you see like a Swiss cheese, it's no problem. Let them shoot it. It's really the places where you don't find bullet holes is where you gotta protect. So in this case, once I look at this, I look at my own work, I realize, well, we're studying genius of the genius and look at nature sciences of discoveries and listen to entrepreneurs who have succeeded and come back and give commencement speeches about you ought to take the risk. You're already naked. What do you have to lose? I think, in this case, the examples are, probably not the same. In the British Navy example, the conclusion got turned 180 degrees. So in reality, it's probably not exactly like that. But the question is, are we so certain all these conclusions based on just observing success would not require any corrections? More broadly, the thinking I want to stimulate within the community was to think about, have we paid enough attention to failures? Okay, so after a couple of years, I'm excited to tell you we start to have some initial understandings of this issue. Today, I'm going to touch on 2 aspects very quickly that broadly improve our understanding around the 2 dimensions. First is to think about, are there impending signals in failures that eventually lead to success? Are there things we can learn from failures that can help us succeed sooner? What are they and how? Second is think about the consequence of failures. Do failures matter? How big of a difference does it make if you fail early in your career? Okay, so I'm going to go through the second question first. I'm going to focus a type of failure that has fascinated me for as long as I can remember. That's called near miss. Near miss is the kind of failure that but didn't quite make it. Okay, so the question is, if you have a near miss early in your career, how much of a difference does it make down the road? Okay, so the opportunity came when NIH came to me and said, what do you think if we give you all our data? I said, that would be fantastic. So that's where, we have about 700,000 competing applications ever submitted to NIH, which is the largest funder for biomedical research in the world. And the data spans about 35 years, and then we can match all these grant applications with all the publication records that we have. What's really interesting about NIH data is how people get funded. For those of you who are not familiar with this, the way NIH funds research is all the proposals come in, they go through the review panels, and they come back with a score, okay? Once you have the score, program manager just line up the score, start to fund the best ones first, one after another, until a certain point, you run out of money. That point is called a pay line, okay? Once the pay line happens, this creates two very interesting souls that interest me for my purpose, which I call near misses and narrow winners. These are the two kinds of people. Here I'm focused on just junior PIs. These are the people who are starting out in their career, starting their lab like 3 years into their lab. And before this day, they're basically what economists call identical twins. Before this day, there's no observable and unobservable difference between the two because it doesn't, it doesn't matter who you are to be above or below that pay line. But after that day, there's a big difference between the two. Narrow winners now have $1 million for the next 5 years to do the research that he or she proposed. Near misses had nothing, right? So the question I want to ask is, let's not hang up on this incident. Let's think into the future. Many years later, when these people come back for a job interview, who do you hire between these two populations? This is a question that used to have a trivial answer, which is you should hire the one who succeeded. Because we know, even if these people are the same, we know rich get richer. Success breeds success. Nothing succeeds like success, right? Okay, but what I wanted to do is let's just look into the data and see how well they publish in the next 5 years and the next 10 years. So here I'm going to use first a ISO standard measure in my field is to say, out of all the papers you publish, how many of them ended up being a hit paper defined as a top 5% citations in the same field and year? Okay, so baseline is 5%. What you're seeing is that narrow winners in the next 5 years publish hit papers about 13%, substantially higher than typical scientists in the field. So this sort of confirms that getting to the pay line at NIH, this is not a walk in the park. I've never get to that close at NIH. So these are really strong people, okay? If you look at near misses, and you see they produce hit papers at about 16%. If you look at the papers from year 6 to year 10, you see a similar gaps sort of persists. But you realize, wait, the near misses are the ones who failed. So paradoxically, they actually systematically outperformed narrow winners in the future. So when I saw these results, I was like, this can't be right. There might be something wrong. So I basically asked my postdoc to try everything that we can think of, resulting in many, many pages of supplementary material. But every time we look at different measurements, we have basically exactly the same conclusions. Okay? So if you look at the number of papers they produce, these two groups, what you see is that they actually produce the similar number of papers. So the overall picture is that near misses had fewer initial grants by construction, but somehow they managed to publish the same number of papers, and most importantly, these papers tend to garner higher impact. So the question is, what is going on here? One pervading hypothesis is called a screening mechanism. The idea here is the following. Early career setback or near misses are actually quite devastating. So when it happens, it actually differentially knock out different group of people. Okay? So now this actually can be validated. So we measure in our data sets, you see every incidence is associated about a 10% attrition rate. This results, by the way, almost gave Francis Collins a heart attack. So they started a working group to think about why so many people got knocked out. But the question is, then validates our underlying assumption is, this raises the question, is this a quit versus great? In other words, is this just a better half of the population that are left? Or these people became a better version of themselves? Okay? So this is, how do we test this question? So obviously it's too late to call these people and say, come back, publish some papers, let's see how well you do. But what we can do is what economists call conservative estimate. What we can do is to artificially remove people from the narrow winner group such that you remove the weakest member from this group first. So you're artificially adjusting an upward adjustment for the performance of narrow winners until you reach the same attrition rate. Okay? Then you can compare this resulting population, the best position to compete with near misses, and see who is doing better. What you see is that after the adjustment, the performance improved, but it wasn't enough to make up the pre-existing gap. So many people say this was providing the first empirical evidence to support Nietzsche's classical phrase of what doesn't kill you makes you stronger. So the take-home message here is to think about failure as a counterintuitive predictor for future success. And quote Shenyang Yamanaka, the father of IPS cells, when he won the Nobel Prize, is to say, I can see any failure as a chance. So lastly, I want to sort of think about, you don't fail just once. You fail over and over, okay? So I'm going to skip this to think about, Michael Jordan's classical phrase of, I fail over and over and over in my life, and that is why I succeed. So we know that success is often preceded by repeated attempts that initially fail. But how exactly do we fail over and over to eventually succeed or not? I'm going to go very quickly through this paper, because this paper actually was published by, with graduate students at IEMS department, Ian Yin, who is on job market right now, published 2019. So here we look at three kinds of repeated failures. One is NIHPS, try to apply for a grant and failed, try again, failed, until they got the grant or not. Second is entrepreneurs, serial entrepreneurs, found a company, didn't exit, another company didn't work, and then until they exit or not. Okay? The third setting, we look at terrorist organizations, where we see terrorist organizations launch an attack, but it didn't kill any, didn't claim any casualties, and then they keep trying until they sort of claim sort of a casualty, until, right, or not. So across these three very different domains, we want to think about other patterns of failure dynamics within these individuals and organizations. And here we want to build a mathematical framework to think about how do you learn from past failure to think about future attempt. What we're seeing here is to think about failure as this wonderful thing that gives you two crucial assets. One is that you failed, that means you tried. So you have some past experience to reuse. Second is you failed, so you have some evaluation, tell you where you did well, you did not so well. So what we're thinking is, what if you look at past failures and think about which are the components I ought to update, which ones we got to keep. If we just think about the simple framework, what we find is that this interesting phase transition, phase diagram, is that how much you learn from past failure does not follow a smooth path, rather an abrupt one characterized by a first-order phase transition. Below the phase transition, what you see is that people are learning from past failure, but they are not learning enough, as if they are not learning at all. Once you learn a little bit more from past failure, you see they cross the phase transition, the learning behaviors start to emerge. You see the time between two consecutive trials start to decrease as a power law, which is signature for learning curves. So what's interesting about phase transition is that small differences can make a big differences in outcome. So what this means is that individuals may have the same characteristics or strategies, but depending on which way of the phase critical points you are, you may face a very different outcome. And what we see is that, despite the simplicity of the model and the diversity of the settings we examine, it seems like all this data offers a set of very consistent patterns. And this is one of them I'm showing here, is if you look at the people who eventually succeed and people who eventually didn't, you see they follow very different trajectory, even though in the beginning they were basically the same in all the several different observable dimensions. So this sort of gets to the idea of a tipping point between success and failure, is that even in the absence of distinguishing characteristics, individuals and organizations may experience fundamentally different outcomes following repeated failures. So here the lesson is to think about this idea that don't just fail fast, but fail faster. Okay, so the idea here is that this is both a strategy and diagnostics. For strategy side, the sort of what this is telling us is you want to think about rapid prototyping, and you want to think about sort of take into account past failures, see what works, and adapt, and eyes on the prize, and try to focus what really needs to be improved. At the same time, failing faster is also a diagnostic, is that if you're not failing faster and faster, maybe you're stuck in the stagnation region. Maybe you're working, not smarter but harder. You just really try different versions, but not learning enough from the past to initiate an intelligent improvement as you fail over and over. Okay, so I want to stop here. I roughly want to thank a range of generous support for the research that make this possible. Most of the